Voyager 1, the most distant human-made object in the universe, is once again sending usable data back to Earth. After months of transmitting only incomprehensible information, the spacecraft has re-established meaningful communication. This breakthrough has rekindled public interest in humanity's longest-running space mission. For decades, we've believed our knowledge of the solar system was nearly complete. But space has a way of humbling us. Just when we think we've uncovered every mystery, new discoveries remind us how little we truly know. One of the most fascinating and mind-bending revelations concerns the Voyager probes and the nature of the vast region that lies beyond our solar system. Launched in the late 1970s, the twin Voyager spacecraft, Voyager 1 and Voyager 2, have pushed the boundaries of exploration farther than anyone could have imagined. Voyager 1 has traveled beyond the heliosphere, the protective bubble created by the sun's solar wind, and now resides in interstellar space. But what's truly astonishing is that our entire solar system, including the distant Oort cloud, appears to be enveloped in an even larger bubble. This mysterious bubble is massive, stretching around 1,000 light-years across. Intriguingly, our sun sits near its center. Could we be trapped inside this enormous cosmic structure? And what does this mean for our understanding of space? These are the questions scientists are now trying to answer. Voyager 1 was launched on September 5, 1977, from Cape Canaveral, Florida, aboard a Titan Centaur rocket. This came just weeks after Voyager 2's launch on August 20th. Initially, both missions were only intended to last 5 years and focus on the gas giants. But these resilient probes have defied all expectations, continuing to transmit data for more than 44 years. The missions were made possible by a rare planetary alignment that occurs only once every 176 years. This alignment allowed the spacecraft to use gravitational slingshots from Jupiter, Saturn, and beyond to propel themselves deeper into space, conserving fuel while gaining speed. Despite being launched after Voyager 2, Voyager 1 reached Jupiter and Saturn first. Voyager 2 took a different trajectory, enabling it to visit Uranus and Neptune as well, making it the only spacecraft to have visited all 4 gas giants. The data collected fundamentally changed our understanding of these distant worlds. Each Voyager carries a golden record, an interstellar message in a bottle. These records contain sounds, greetings, and music from Earth, intended as a cosmic hello to any intelligent beings who might one day encounter the spacecraft. It's a poetic reminder that exploration is as much about storytelling as it is about science. As of January 2024, Voyager 1 sits approximately 14.9 billion miles away from Earth, roughly 158 times the distance from Earth to the Sun. Voyager 2, while slightly behind, also achieved a historic milestone by crossing into interstellar space in November 2018, 6 years after Voyager 1 did the same in August 2012. Voyager 1's crossing into interstellar space was confirmed through data from its plasma wave instrument. Between April and May 2013, this instrument picked up a massive solar eruption that caused nearby electrons to oscillate. These vibrations allowed scientists to measure the density of the surrounding space, which turned out to be much higher than within the heliosphere. This confirmed that Voyager 1 had exited the heliosphere on August 25, 2012. Voyager 2's plasma data later supported these findings, cementing the moment as one of the most important milestones in space exploration. Although both spacecraft ventured into similar territory, their journeys revealed different data points. This raised compelling questions about how the Sun moves through the galaxy and how the heliosphere responds to its environment. The edge of the heliosphere, called the heliopause, is a dynamic and ever-changing boundary where solar wind and interstellar medium collide. The Sun isn't stationary. It hurtles through the galaxy at approximately 450,000 kilometers per hour. It's essentially a giant nuclear furnace emitting a constant stream of charged particles known as the solar wind. These particles form a magnetic bubble around the solar system, the heliosphere. The heliosphere is a vital shield. It protects planets, moons, and all life from the harshest radiation in the galaxy. Without it, Earth and its neighbors would be vulnerable to cosmic rays and other high-energy particles that can cause severe biological and technological damage. Understanding the heliopause is key to studying not only our solar system, but also how other stars and their planetary systems might behave. The data from the Voyager spacecraft helps scientists examine the mixing of solar wind and interstellar material. These interactions offer clues about the galaxy's structure and the forces at play within it. When Voyager 1 crossed the heliopause, it encountered interstellar magnetic fields that were 2 to 3 times stronger than expected. These fields exerted up to 10 times more pressure on the heliosphere than previously estimated. Unfortunately, Voyager 1's plasma instrument had failed in 1980, leaving a data gap. Voyager 2, with its plasma instrument still functional, provided the breakthrough. It revealed how plasma near the heliopause became hotter, denser, and slower, a clear sign of the transition from solar to interstellar space. The heliopause was not a solid wall, but a porous, flexible boundary allowing particles to pass through both ways. Interestingly, Voyager 1 had detected 10 separate streams of interstellar particles penetrating the heliopause even before it fully crossed the boundary. Voyager 2 added to this knowledge by discovering a faint flow of low-energy particles more than 100 million kilometers beyond the heliopause. As the spacecraft approached the boundary, their data revealed a transition zone. For Voyager 1, the solar wind slowed to a crawl, creating a strange limbo-like state. Voyager 2 saw a similar transitional layer, but with key differences, underscoring the heliosphere's complexity. Both probes exited the heliosphere at different locations, Voyager 1 at the leading edge and Voyager 2 at the flank. However, neither spacecraft has passed through the wake of the heliosphere, leaving questions about its overall shape. Some models suggest a spherical bubble, while others propose a comet-like or glass-shaped structure. Current spacecraft cannot resolve this mystery. Even New Horizons, one of the fastest spacecraft ever launched, will run out of power in the 2030s, over 1 billion miles short of the heliopause. This limitation has prompted growing interest in a next-generation interstellar probe. More data points are necessary to fully understand the heliosphere's shape and dynamics. Without them, scientists can only speculate. Still, the Voyagers continue to provide surprising insights. One of Voyager 1's strangest findings was a low-frequency hum beyond the heliopause. This hum is believed to be caused by oscillations in the interstellar plasma, triggered by solar activity. Unlike the sudden bursts observed during solar storms, this signal is continuous. It suggests a more subtle and persistent activity within the interstellar medium than scientists had anticipated. By studying this hum, researchers can map the distribution of plasma in the far reaches of space. It also helps refine models of how the solar wind interacts with interstellar particles. The Voyager missions are teaching us that interstellar space is not a void, but a dynamic environment full of interactions. In the past, scientists could only detect interstellar plasma during rare events like solar eruptions. Now, thanks to the Voyager probes, they can study this environment in more detail and over longer periods of time. Even decades after launch, the Voyagers are making headlines. One such moment came in 2024 when Voyager 1 experienced a major communication issue. Its primary X-band transmitter suddenly stopped working, cutting off the flow of data. Engineers detected a faint signal, coming from a backup S-band transmitter that hadn't been used since 1981. Astonishingly, this backup transmitter, dormant for over 43 years, sprang back to life. Designed as a fail-safe system, it proved the brilliance of Voyager's engineering. Though weaker and less detailed, the S-band signal allowed NASA to confirm that Voyager 1 was still functioning. This fallback system was likely activated by the spacecraft's onboard fault protection software, which is programmed to respond to malfunctions by switching to backup systems. However, the S-band transmitter cannot relay detailed telemetry. NASA is now exploring whether the original X-band system can be restored without risking the spacecraft's stability. Deep space communication presents unique challenges. Commands take nearly 2 days to travel to the spacecraft and back, meaning every adjustment must be carefully planned and executed. Despite these limitations, the team has kept the mission alive for nearly half a century. What's next for the Voyagers? Although their power sources are expected to fade within the next few years, the spacecraft will continue drifting silently through space. In about 1 billion years, they will be tens of thousands of light years from the Sun. ghosts of humanity's curiosity flying between the stars. Voyager 1 is currently heading toward a star designated AC plus 793888, while Voyager 2 is on a course toward Ross 248 in the Andromeda constellation. Neither will get close to these stars for at least 40,000 years. By then, they will be inactive relics, carrying their golden records like silent ambassadors from Earth. Even after their instruments shut down, the Voyager spacecraft will remain symbols of our drive to explore. And perhaps the most exciting discoveries, those we haven't yet imagined, still lie ahead. As long as they travel, they will represent the farthest reach of human endeavor.